GraphQL, the Modern API Handbook. Chapter 1, The API Revolution, Why GraphQL Matters. Imagine you're at a restaurant, eager to order a meal. In the old days, you might have to shout your order across a crowded room, hope someone hears you, and then wait for them to decide what they think you want to bring you. Sometimes you'd get too much food, sometimes not enough, and sometimes it would be entirely wrong, forcing you to shout again for corrections. In the world of software, this clumsy ordering process was once the norm for how different parts of an application, or even different applications entirely, talk to each other. This communication happens through something called an API, short for Application Programming Interface. Think of an API as the detailed menu and the well-organized waiter at your preferred restaurant. It defines the specific ways you can request information or services, and how the kitchen, the server, will respond. For years, the dominant way to design these digital menus was through what's known as REST, representational state transfer. REST APIs became incredibly popular because they were straightforward, leveraging the familiar structure of the web itself, particularly HTTP, the protocol that powers everything you see in your browser. With REST, if you wanted information about a user, you'd make a request to a specific user address. If you wanted their posts, you'd make another request to a post's address. It was simple, predictable, and highly effective for many situations. However, as applications grew more complex, especially with the explosion of mobile devices and dynamic web experiences, the elegance of REST began to show its limitations. Picture this: you're building a social media app. On the main feed, you want to show a user's name, their profile picture, their latest post, the number of likes on that post, and a snippet of the first comment. With a traditional REST API, this single view might require multiple orders. A request to /users/ID to get the user's name and profile picture. Another request to /users/ID/posts to get their latest post. Then perhaps posts/ID/likes to get the like count. And yet another to posts/ID/comments to get the comment snippet. Each of these is a separate trip to the server, adding latency and requiring your app to piece together information from various sources. This is like going to a deli and buying only the cheese, then going to a bakery for the bread, and then a butcher for the ham, when all you wanted was a simple sandwich. Worse, what if the /users/ID endpoint gives you all the user's details, their email, addresses, phone numbers, and job history, when your feed only needed their name and picture? This is called overfetching, getting more data than you actually need. It wastes bandwidth, slows down your application, and puts unnecessary strain on your server. Conversely, underfetching happens when a single request doesn't give you everything, forcing you to make multiple requests, as in our social media example. Both lead to inefficient applications and frustrated developers. This is exactly the scenario that Facebook faced in 2012. Building a massive, evolving mobile application, they found that their traditional API approach was struggling to keep up with the rapid pace of change and the diverse data needs of different parts of their app. They needed a more efficient, flexible, and powerful way to query their data. And so, they invented GraphQL. GraphQL, which stands for Graph Query Language, isn't just another technology. It's a fundamental shift in how APIs are designed and used. At its core, GraphQL allows the client, whether it's your mobile app, your web browser, or another server, to ask for exactly what it needs and nothing more. Instead of making multiple requests to predefined endpoints, a client sends a single, precise query to your GraphQL API, describing the data structure it expects back. Imagine our social media feed again. With GraphQL, your app would send just one request, detailing every piece of information it requires. Give me the user's name and profile picture, and their latest post's content, and the number of likes on that post, and the text of its first comment. The server then responds with only that exact data, all in one neat package. This is the aha moment of GraphQL, delivering the precision and efficiency that modern applications demand. The beauty of GraphQL lies in its flexibility. Different parts of your app can ask for different combinations of data from the same API without the server needing to change. Mobile clients might need less data for performance, while desktop clients might demand more. GraphQL caters to both, dynamically. It treats your entire data landscape as a single, interconnected graph, allowing you to navigate and retrieve information with unparalleled granularity. In the chapters that follow, we will peel back the layers of GraphQL, understanding its fundamental components, how you define your data, craft powerful queries, manipulate information, and even receive real-time updates. We'll explore how to build and consume GraphQL APIs, and finally, delve into advanced topics like performance and security. By the end of this book, you'll not only understand why GraphQL is revolutionizing the API landscape, but you'll also be equipped to leverage its power in your own projects. Welcome to the Modern API Handbook. Chapter 2, A Brief History of APIs, from REST to GraphQL. To truly appreciate why GraphQL has stirred such significant excitement, it's helpful to understand the landscape it emerged from. The world of application programming interfaces, or APIs, has a rich history, constantly evolving to meet the demands of increasingly complex and interconnected software systems. In the early days of networked computing, different systems communicating might have involved complicated, low-level protocols tailored to specific needs. As the internet matured, the need for standardized ways for machines to talk to each other became clear. One of the earliest widespread attempts at a structured approach was SOAP, Simple Object Access Protocol. SOAP, based on XML, offered a highly rigid and robust framework for defining messages and interactions. Think of SOAP as a meticulous, formal diplomat, ensuring every word and gesture adheres to strict protocol. While powerful, its complexity, verbosity, and reliance on XML made it cumbersome for the rapidly developing web. Setting up a SOAP client and server often felt like assembling a sophisticated piece of machinery just to send a simple message. Then came the rise of the web and the burgeoning ecosystem of interconnected services. This environment demanded something simpler, more lightweight, and aligned with the pervasive HTTP protocol that already powered web browsers. Enter REST, Representational State Transfer. Articulated by computer scientist Roy Fielding in his doctoral dissertation in 2000, REST wasn't a protocol like SOAP, but rather a set of architectural principles for designing networked applications. REST proposed treating everything on the web as distinct resources. Each resource could be identified by a unique URL, much like a file or page has a web address. To interact with these resources, you would use standard HTTP methods. Get to retrieve a resource, like reading a web page. Post to create a new resource, like submitting a form. Put to update an existing resource, like editing a document. Delete to remove a resource. These principles led to APIs that were intuitively understandable for anyone familiar with the web. Want to get a list of products? Get products. Want to add a new product? Post products. This simplicity, combined with the fact that it leveraged existing web infrastructure, made REST the dominant standard for several years. It became the Swiss Army knife of API design, versatile, widely understood, and capable of handling a vast array of tasks. REST APIs fueled the explosion of mobile applications, allowed different companies to share data seamlessly, and underpinned many of the internet services we use daily. Companies like Twitter, Google Maps, and countless others expose their functionalities through REST-TFL interfaces, enabling developers to build entirely new applications on top of their services. However, even the most versatile tools have their limitations when confronted with new challenges. As applications became more dynamic, interactive, and relied heavily on fetching data from multiple sources, some inherent characteristics of REST began to strain. Consider an e-commerce application. A product detail page might need the product's core information, name, description, price, its images, customer reviews for that product, related products based on purchase history, inventory levels from a separate system. With a purely REST-TFL approach, this typically means a series of distinct requests. Get/products/ID, get/products/ID/images, get/products/ID/reviews, get/products/ID/related, get/inventory/product ID. This often led to the underfetching problem discussed in Chapter 1, multiple round trips from the client to the server. each adding latency and complexity to the client-side code responsible for orchestrating these requests and stitching the data together. For mobile networks, where bandwidth is often limited and latency higher, these multiple round trips could significantly degrade user experience. Conversely, REST APIs often suffer from overfetching. If calling /product/ID returns every single detail about the product SKU, supplier ID, manufacturing date, internal pricing tiers, but your product page only needs the name and description, you're pulling down a lot of unnecessary data. This wastes bandwidth and processing power on both the client and server. Another challenge for REST was versioning. As APIs evolve, what happens when you need to add new fields or change existing ones? Do you create V1 products and V2 products? This can lead to API sprawl and maintenance headaches for both the API provider and consumers. These growing pains became particularly acute for large organizations building complex, interconnected services, especially those with diverse client applications. Web, iOS, Android that each had slightly different data needs. Facebook, with its enormous user base and constantly evolving product features, felt these limitations acutely. Their mobile app, in particular, was pulling data from many disparate backend services, and orchestrating these multiple REST calls was becoming a bottleneck for development speed and application performance. It was out of this specific need, the quest for more efficient data fetching, greater flexibility, and a streamlined developer experience, that GraphQL was born at Facebook in 2012. It was subsequently open-sourced in 2015, sharing its revolutionary approach with the wider development community. The core idea behind GraphQL is to give the client declarative control over the data it receives. Instead of the server defining a fixed set of endpoints with predefined data structures, the client now literally declares what data it wants, and the server figures out how to fulfill that request. This fundamental shift from resource-oriented APIs, REST, to query-oriented APIs, GraphQL, is the genesis of what we will explore in the coming chapters, starting with the very language of GraphQL itself, its queries, mutations, and subscriptions. Chapter 3, the core of GraphQL, queries, mutations, and subscriptions. Every powerful system has foundational elements, and for GraphQL, these are its three primary operations: queries, mutations, and subscriptions. These aren't just technical terms, they represent the complete vocabulary your client applications use to talk to your GraphQL API. Think of them as the three main verbs in the GraphQL language, allowing you to read data, change data, and listen for real-time updates. A unique and unifying aspect of GraphQL is that, regardless of the operation type, all interactions happen through a single endpoint. Unlike REST, where you might have dozens or even hundreds of distinct URLs, users, products, orders, posts, etc., a GraphQL API typically has just one URL. All requests, whether they are reading, writing, or subscribing, are sent to this single point. This simplifies client-side configuration and centralizes your API's entry point. Let's dive into each operation. Queries. Reading data with precision. If a GraphQL API is a vast library of information, a query is how you ask the librarian for exactly what you need. It's the operation for reading data. The magic of GraphQL queries lies in their ability to let you specify precisely which fields and nested properties you want to retrieve. Nothing more, nothing less. Consider a simple example. If you want to get a user's name, query user ID 123, name. The server would respond with something like data, user, name, Alice. Notice a few key things. We explicitly state query to indicate our intention, though for simple read operations, it's often optional. We use curly braces to define the structure of our request. We specify the user field, pass an id argument, and then nest the name field inside it. This is the precision at play. If we also wanted their email, we'd simply add email to the request, and the server would provide it. This nested structure is incredibly powerful. You can fetch a user's name, their last 3 posts, the comments on those posts, and the authors of those comments, all in a single query. This capability directly tackles the underfetching problem common with REST APIs. Mutations. Changing data safely. If queries are about reading, mutations are about writing data. They are how you create new records, update existing ones, or delete information from your server. Mutations follow a very similar syntax to queries, but explicitly state their intent using the mutation keyword. Think of a mutation as placing a specific order with the chef to change something in the kitchen. Once the change is made, you can also ask for specific confirmation back. To create a new user, you might send a mutation like this. Mutation. Create user name, Bob email, bob@example.com. id, name, email, and the server might respond. Data. Create user, id 456. Name, Bob. Email, bob@example.com. Here, create user is the name of our specific mutation operation. We pass in the name and email as arguments. Crucially, after the user is created, we ask the server to return the id, name, and email of the newly created user. This allows the client to immediately update its local state without needing to make a subsequent query. This immediate feedback loop is a key advantage of GraphQL mutations. Common uses for mutations include: sign up username, password to create a new user account, update user profile, ID new bio to modify user data, delete product, ID to remove an item from a catalog, place order items, shipping address to finalize a purchase. Mutations are designed to be explicit and typically represent side-effecting operations, i.e., they change data on the server. While you could technically make a create operation a query, GraphQL best practices dictate that any operation that changes server data should be a mutation, making your API more predictable and easier to understand. Subscriptions, real-time data updates. For applications that demand live, dynamic, and responsive user experiences, subscriptions are the answer. They allow clients to receive real-time updates from the server whenever specific data changes. If queries are like reading a book and mutations are like writing a chapter, subscriptions are like getting a notification every time a new book by your favorite author arrives at the library. Subscriptions typically operate over a persistent connection, most commonly using the WebSockets protocol. This means that once a subscription is established, the client doesn't need to constantly ask for updates, known as polling. Instead, the server pushes relevant data to the client as soon as it becomes available. Imagine a chat application. You want to know immediately when a new message is posted in a channel. A subscription would look conceptually similar to a query. Subscription. New message chat room ID. General. id. Text. User. Username. Once this subscription is active, every time a new message is posted in the general chat room, the GraphQL server would send a data payload to the subscribing client, containing the id, text, and user information of the new message. Common use cases for subscriptions include live chat messages or comments, real-time notifications, e.g., a friend liked your post, tracking live data streams, e.g., stock prices, sports scores, collaborative editing, where changes need to be reflected instantly. While powerful, subscriptions introduce architectural considerations for the server, such as managing active connections and efficiently publishing data to many subscribers. We'll delve deeper into the implementation details of all these operations in later chapters. In summary, queries, mutations, and subscriptions form the bedrock of GraphQL. They provide a unified, intuitive, and highly efficient language for clients to interact with your API, allowing for precise data fetching, safe data manipulation, and dynamic real-time experiences, all through that single, powerful GraphQL endpoint. With this fundamental understanding, we can now turn our attention to the blueprint that defines these interactions, the GraphQL schema. Chapter 4, Defining Your Data. Mastering the GraphQL Schema Definition Language, SDL. Imagine you're an architect designing a building. Before any construction begins, you create a detailed blueprint. This blueprint specifies every room, their dimensions, where the doors and windows are, what materials will be used, and how everything connects. Without this clear plan, construction would be chaotic, and the final building might be unstable or unusable. In the world of GraphQL, the schema is that blueprint. It is the central, definitive contract between your client applications and your GraphQL server. It precisely describes all the data that clients can query, all the modifications they can make, and all the real-time updates they can subscribe to. It defines the types of data that exist in your API, the relationships between them, and what operations are possible. This schema is written using the Schema Definition Language, SDL. SDL is a human-readable, plain-text language specifically designed for defining GraphQL schemas. Its simplicity and clarity make it easy for developers to understand the API's capabilities just by reading its schema. Let's break down the fundamental building blocks of the GraphQL Schema Definition Language, the building blocks of SDL. At its most basic level, a GraphQL schema is built upon types. One, scalar types, the atoms of your data. Scalar types are the fundamental atomic units of data that cannot be broken down further. GraphQL provides a set of built-in scalar types: string, a sequence of characters, e.g., hello world; int, assigned 32-bit integer, e.g., 123-45; float, assigned double precision floating point value, e.g., 3.14 1.0; boolean, true or false; ID, a unique identifier, often represented as a string. It's automatically serialized as a string, but carries a semantic meaning indicating it's an ID. GraphQL servers might treat ID fields differently for caching or uniqueness. These are your basic ingredients, like numbers, words, and true-false statements. 2, object types, structuring your data. Most of the data you work with will involve custom structures. These are defined using object types. An object type represents a collection of fields. Each field has a name and a type. Let's define a user type, type user. ID name, string, email, string. Age, int. In this example, type user declares a new object type named user. ID, the user type has a field named id, its type is ID. The exclamation mark means this field is non-nullable, it must always have a value when requested. Name, string. The name field is a string and is also non-nullable. Email, string. The email field is a string but is nullable, no. This means an email value might or might not be present. Age, int. The age field is an int and is also nullable. Object types can also have fields that are other object types, allowing for complex, nested data structures. Type post. ID title, string, content, string. Author, user. The author is a user object. Likes, int, published at, string. Here, post has an author field, which is of type user. This allows clients to ask for a post and immediately its author's details in a single query. 3, lists. Handling collections of data. To represent a collection of items, like a list of posts or a list of comments, you use square brackets around the type. For example, type user. Other fields, posts, post. A list of posts. The list itself is non-nullable, and each item in the list must be a non-nullable post. This definition means a user object has a posts field, which is a list, array of post objects. The outer means the posts list itself cannot be null, a user always has a posts field, even if it's an empty list. The inner means that each item within that list must be a non-null post object. 4, arguments. Customizing field behavior. Fields can accept arguments that allow clients to customize the data they receive. This is how you filter, sort, or paginate data. Arguments are defined using parentheses after the field name with a name and a type. Type query, this is a root query type, more on this next. Post ID. Post get a single post by its ID. Posts limit, int offset, int post. Get a list of posts with optional limit and offset. In the posts field, limit and offset are arguments of type int. Root operation types. The entry points to your API. While you can define many custom object types, your GraphQL API needs specific entry points where clients can begin their operations. Queries, mutations, and subscriptions. These are defined by special root types. Query type. This is the mandatory root type for all read operations. All fields directly at the top level of your query type are the available queries clients can make. Type query. Users, user. User ID, user. Posts, post, other query fields. A client can then send a query like query user ID. 123, name or query posts, title. Mutation type. This is the root type for all create, update, and delete operations. Type mutation. Create user name, string, email, string, user, update post, ID, title, string content, string post. Delete user ID, Boolean hash, other mutation fields. Note the input arguments like name, string for create user. Often, for more complex mutations, you'll see input object types, e.g., create user input, create user input, user, which are similar to regular object types but specifically designed to be passed as arguments. Subscription type, optional. This is the root type for real-time data updates. Type subscription, new post, user updated ID, user hash, other subscription fields. When a client subscribes to new post, the server will push a post object to the client whenever a new post is created. Finally, your schema usually includes a schema declaration that specifies these root types, though many GraphQL implementations will infer them if they follow the standard naming conventions: query, mutation, subscription. Schema, query, mutation, subscription. The power of an explicit schema. The explicit nature of the GraphQL schema is one of its greatest strengths. Validation. The server uses the schema to validate every incoming request. If a client asks for a field that doesn't exist or provides an argument of the wrong type, the server can immediately reject the request before attempting to fetch any data. Documentation. The schema is self-documenting. Developers can easily explore all available types, fields, and operations. Tools like GraphQL or Apollo Studio can read your schema and provide interactive documentation and auto-completion for queries. Tooling. The schema enables a rich ecosystem of developer tools. Client-side libraries can generate type-safe code, helping to catch errors at compile time rather than runtime. Server-side tools can help ensure your resolvers correctly implement the schema's promises. Discoverability. Front-end developers can autonomously explore the API and understand its capabilities, reducing reliance on backend teams for specific API documentation. Mastering the SDL is key to building effective, maintainable, and understandable GraphQL APIs. It's the language you'll use to describe the world of data your API governs, ensuring that everyone, from the client requesting data to the server providing it, is on the same page. With this blueprint in hand, we are now ready to craft the requests that bring our data to life, the GraphQL queries. Chapter 5, Fetching Data with Precision, Crafting Powerful GraphQL Queries. In the previous chapter, we learned about the GraphQL Schema Definition Language, SDL, the blueprint that defines the entire structure of your API. Now, it's time to put that blueprint to work. This chapter dives deep into GraphQL queries, showing you how to ask for exactly the data you need from your API, nothing more, nothing less. Think of a GraphQL query as a very specific shopping list you hand to a highly efficient personal shopper. Instead of getting a box of random groceries, you get only the kale, organic eggs, and artisanal bread you specifically requested. This precision is what makes GraphQL so powerful. Basic query syntax, fields, and selection sets. At its simplest, a GraphQL query just asks for fields. A query is always structured within curly braces. Inside these braces, you list the top-level fields you want to retrieve. The server will then return the data for those fields. Let's assume our schema has a query type with fields like users, which returns a list of users, and me, which returns the currently logged-in user. To get the name of the current user, query me, name. The response would look something like data, me, name, Alice. If we wanted more details about Alice, we simply add more fields to the selection set. Query me, name, email, a. This flexibility stands in stark contrast to preset REST endpoints, where you'd get whatever the me endpoint decided to send, often leading to overfetching. Nested queries. Retrieving related data in one go. One of GraphQL's most compelling features is its ability to retrieve nested, related data in a single request. This capability is a game changer for reducing network round trips and simplifying client-side data management. Recall our user and post types from the schema. Type user. ID name string, posts post. Type post, id title, string, author, user. Now, imagine you want to fetch a user's name and the titles of all their posts. In REST, this would typically involve two separate calls. In GraphQL, it's one query, user ID, 123, name, posts, title, id. The response would elegantly combine this data. Data, user, name, Bob, posts, title, my first blog post, id, P1, title, thoughts on GraphQL, id, P2. You can nest as deeply as your schema allows, following the relationships between your types. For instance, if post also had comments, you could ask for the post title and the content of its comments, and even the author of each comment. Arguments, filtering and customizing data. Fields in a GraphQL query can accept arguments, allowing you to pass parameters to customize the data you receive. This enables filtering, sorting, pagination, and many other dynamic behaviors. Arguments are specified in parentheses, after the field name, to fetch a specific user by their ID. Query. User ID 123. #id is an argument with value 123. Name. Email. To limit the number of posts returned or get a specific range. Query. Posts limit 5 offset. 10 #limit and offset are arguments. Title. The specific arguments a field accepts are defined in the schema, as we saw in Chapter 4. Aliases, renaming fields in the response. Sometimes, you might need to query the same field multiple times within a single query, but with different arguments. For example, if you want to get details for two different users. Query. This would cause a conflict, because both would return a field named user. #user ID 1, name. #user ID 2, a name. #use aliases to resolve the conflict. First user, user ID 1, name. Second user, user ID 2, name. By adding first user and second user before the field, you tell GraphQL to rename the output JSON field to that alias. Response. Data. First user, name, Alice. Second user, name, Bob. Fragments, reusable query components. As queries grow in complexity, you might find yourself repeating the same sets of fields across different parts of your application, or even within the same query. Fragments solve this by allowing you to define reusable units of fields. Think of a fragment as a reusable snippet for a particular shape of data. Fragment user details on user. Id, name, email, query, me, ... user details #, use the fragment here. User ID 456, ... user details # and again here. In this example, user details is defined as a fragment on user, meaning it can only be applied to fields that return a user type. When the query is executed, ... user details will be expanded to id, name, and email. Fragments greatly improve the readability, reusability, and maintainability of your queries. Variables. Dynamic query execution. Hard-coding values directly into queries, especially for arguments, is often impractical for real-world applications. You rarely know a user's ID or a post's title when writing the query. Variables allow you to parameterize your queries, making them dynamic and reusable. To use variables, you define them at the top of your query with a prefix and their type, e.g., userid, ID. Then you pass them alongside your query when sending the request, usually in a separate JSON object. Query get user and posts, $user ID, post limit $, int, user ID, userid $, name, email, post limit $, title, and you'd send this along with a variable's JSON object. Userid 123, post limit 3. Variables prevent injection vulnerabilities and allow client-side frameworks to easily generate and execute queries with dynamic data. Operation names, improving readability and debugging. While optional for simple queries, giving your queries an operation name is a good practice. It improves readability, especially for complex queries, and can be invaluable for debugging error messages, as the name will typically be included in server logs. Query fetch user profile and recent posts. This is the operation name. User ID 123. Name, email, posts limit 5. Title, directives, conditional inclusion of fields. GraphQL also includes built-in directives like @include and @skip, which allow you to conditionally include or exclude fields or fragments based on a Boolean value. Query conditional user field $with email, Boolean. User ID, 123. Name, email @include if. With email $, hash only include email if with email is true. If with email is true, email is returned. If false, it's not. This allows clients to build flexible UI components that can dynamically request different data based on user preferences or application state, without requiring multiple distinct queries. Conclusion: crafting GraphQL queries is a fundamental skill that unlocks the full potential of your API. The ability to precisely request data, combine related information, filter with arguments, and use reusable fragments and dynamic variables empowers client-side developers to build efficient, fast, and highly responsive applications. This precision directly translates to fewer network requests, less data transfer, and a smoother user experience, making GraphQL an invaluable tool in the modern web development toolkit. Next, we'll explore how to change this data using mutations. Chapter 6, Changing Data Safely, Understanding GraphQL Mutations. If GraphQL queries are how you elegantly fetch data, mutations are how you orchestrate changes to that data. When you need to create a new user, update a product's description, delete a record, or trigger any action that alters the state of your backend, you'll use a GraphQL mutation. Just as a query is like ordering food from a menu, a mutation is like phoning in an alteration to your order, perhaps adding extra cheese, canceling an appetizer, or changing your reservation time. The key difference is that a mutation tells the server to do something, rather than just get something. The purpose and structure of mutations. The primary purpose of a mutation is to enable operations that have side effects on the server's data. This includes creating new data, e.g., create user, add post, updating existing data, e.g., update product price, modify user email, deleting data, e.g., delete comment, remove user, triggering an action that changes state, e.g., place order, process payment. Syntactically, mutations are very similar to queries. They use the same curly brace structure, selection sets, and arguments. The main distinguishing factor is the explicit use of the mutation keyword at the beginning of the operation. Let's revisit our user and post examples. Imagine we want to create a new user. Our schema might define a mutation type like this: type mutation. Create user name, string, email, string age, int, user. To execute this mutation and create a new user named Charlie. Mutation, create no user. Create user name, Charlie, email, charlie@example.com, age 30. Id, name, email. After the server successfully creates Charlie, it returns the id, name, and email for the newly created user as specified in the selection set. This is incredibly powerful. You not only perform the action, but also get immediate confirmation and the updated data without needing a separate query. This capability often simplifies client-side logic significantly. Best practice, input types. For mutations that involve multiple arguments, particularly when creating or updating complex objects, directly listing all arguments can become unwieldy. GraphQL offers a structured solution through input types. Input types are special object types, also defined in SDL, that are designed to be passed as arguments to fields. They are typically prefixed with input to distinguish them from regular object types. Example, input type. Input, create user input. Name, string, email, string. Int. Now, our create user mutation in the schema can use this input type. Type mutation. Create user input, create user input, user. And the mutation query itself becomes cleaner. Mutation, create no user. Create user input. Name, David. Email, david@example.com. Age, 25. Id. Name, email. Input types improve readability, promote reusability of argument structures, and make it easier to add new fields to a mutation input in the future without breaking existing clients, as long as new fields are nullable. Understanding the return payload. As seen in the Create User example, mutations allow you to specify a return payload, the data you want to receive back after the mutation is performed. This is not just a confirmation message. It's a full GraphQL selection set, identical in form to a query. Consider an update post mutation, type mutation. Update post ID, ID title, string content, string post. If you want to update a post's title and immediately see the new title along with its ID and the author's name, mutation update post title. Update post ID, P1 title. My new blog post title. ID, title, author, name. The response would give you precisely that. Data, update post, ID P1, title, my new blog post title, author, name, Bob. This immediate feedback is a significant benefit, allowing clients to refresh their UI or local state without needing to trigger separate data fetches. Error handling in GraphQL mutations. Error handling in GraphQL mutations often takes a different approach than traditional REST APIs. While HTTP status codes are still relevant, e.g., a 200 OK for a successful GraphQL request, a 400 bad request if the query is malformed, application-level errors, like validation failures or business logic errors, are typically returned within the GraphQL response payload itself. This approach acknowledges that a GraphQL request can involve multiple operations, and some might succeed while others fail, or a failure might occur after parsing the request itself. A common pattern for returning errors within a mutation payload is to include an errors field in the response, alongside the data field, or to structure the mutation return type to explicitly include error details. Example with explicit error handling in the data payload. Schema for login mutation, type login payload. Token, string. User, user. Errors, user error. Type user error. Field, string. Message, string. Type mutation. Login username, string, password, string. Login payload. Successful login mutation. Mutation user login. Login username. Valid user, password. Valid password. Token. User. ID. Name. Errors. Field. Message. Successful response. Data. Logins. Token, token here. User. ID. U123. Name, valid user. Errors. Null. Failed login due to invalid credentials. Data. Logins. Token, null. User, null. Errors. Field, password. Message, invalid username or password. This approach allows clients to process the response gracefully, distinguishing between network parsing errors, which might result in a non-200 HTTP status, and application-specific business logic errors. Naming conventions for mutations. While not strictly enforced by GraphQL, following clear naming conventions significantly improves the readability and maintainability of your API. Common patterns include create resource name, create user, create product, update resource name, update user, update product price, delete resource name, delete user, delete comment, action name, login user, add items to cart, process payment. By adhering to these conventions, developers can quickly understand the intent and expected behavior of each mutation. In summary, GraphQL mutations provide a structured, predictable, and powerful way to modify data on your server. By explicitly defining input arguments and precisely specifying the data you want returned in the payload, mutations streamline client-server interactions, reduce network traffic, and enhance the overall developer experience. With queries for reading and mutations for writing, the final core operation we'll examine in the next chapter is how to handle real-time data flow with subscriptions. Chapter 7. Real-time data. Embracing GraphQL subscriptions. Most applications for a long time have operated on a request-response model. The client asks for data, a query, the server sends it back. Or the client tells the server to change data, a mutation, and the server confirms the change. This model works well for many scenarios, but it falls short when you need immediate, live updates without constantly asking for them. Imagine a world where you have to keep repeatedly checking your mailbox to see if you have new mail, or incessantly refreshing your website to see if a new news article has been published, or if someone has commented on your post. This inefficient practice, known as polling, consumes unnecessary resources and introduces delays. For modern interactive applications, such as chat apps, live dashboards, stock tickers, or multiplayer games, data needs to flow seamlessly and instantly from the server to the client as soon as it becomes available. This is where GraphQL subscriptions step in. What are GraphQL subscriptions? If a query is like asking for exactly what you need right now, and a mutation is like telling the server to do something, a subscription is like telling the server, notify me whenever this specific event happens. Unlike queries and mutations, which are typically short-lived HTTP requests, subscriptions establish a persistent, long-lived connection between the client and the server. Once the connection is established, the server can actively push data to the client whenever the subscribed event occurs. This pushing mechanism is primarily achieved using the WebSockets protocol, which provides a full duplex communication channel over a single TCP connection. How subscriptions work. The life cycle of a GraphQL subscription typically involves these steps. Subscription request. The client sends a subscription query to the GraphQL server, similar in syntax to a query or mutation, using the subscription keyword. Connection establishment. The server receives the subscription request. If it supports subscriptions, which usually means WebSockets are enabled, it establishes a WebSocket connection with the client. Event listening. The server listens for the specific event or data change described in the subscription query. This might involve internal data sources, message queues, or event streams. Data push. When the relevant event occurs, the server executes the subscription's associated resolver, fetches the requested data, and pushes the data payload over the established WebSocket connection to the client. Client update. The client receives the pushed data and can immediately update its UI or application state to reflect the real-time change. Connection termination. The connection remains open until either the client explicitly closes it, the server closes it, or an error occurs. Subscription syntax. The syntax for a subscription is familiar, much like queries and mutations, but starts with the subscription keyword. Let's define a subscription for a new post being added. Type subscription. New post, post. A client would subscribe like this. Subscription, new post, subscription. New post. Id. Title. Author. Name. Every time a new post is created on the server, presumably through a mutation like create post, the server would then send a data payload resembling this through the WebSocket connection to all clients subscribed to new post. Data. New post. Id. New posted. Title, a fresh new article. Author, name, Jane Doe. Just like queries, subscriptions can also take arguments to filter which events you want to be notified about. For instance, subscribing to new messages in a specific chat room. Type subscription. Message added, chatroom ID, message. Client subscription. Subscription chat message subscription, $room ID. Message added, chatroom ID, roomid $. Id. Text. Sender. Username. This allows a client to only receive messages relevant to the chat room they are currently viewing. Common use cases for subscriptions. The applications for GraphQL subscriptions are vast and growing. Chat applications, real-time delivery of new messages, typing indicators, and user online/offline status. Live dashboards analytics, instantly updating charts and metrics as data flows in. Gaming, propagating game state changes, player movements, or score updates. Notifications, pushing immediate notifications to users about new activity, e.g., a friend request, a comment on their post. Collaborative editing, synchronizing changes across multiple users editing the same document. Booking reservation systems, notifying users about changes in availability or booking status. Challenges and considerations. While powerful, implementing and scaling GraphQL subscriptions introduces complexities that are not present with traditional HTTP-based queries and mutations. WebSocket management. The server must manage numerous persistent WebSocket connections efficiently. This requires robust infrastructure to handle connection resilience, authentication over WebSockets, and disconnections. PubSub mechanism. To efficiently publish data to potentially thousands of subscribers, servers typically integrate with a publish-subscribe PubSub system. This could be an in-memory PubSub for smaller applications, or external services like Redis PubSub, Apache Kafka, or cloud-managed messaging queues for distributed and scalable solutions. Scalability. As the number of concurrent users and real-time events grows, the server needs to scale horizontally. This means coordinating multiple server instances to ensure that events are published to all relevant subscribers, regardless of which server instance they are connected to. Security. Authentication and authorization details need to be managed for persistent WebSocket connections, ensuring that only authorized users receive specific real-time data. These challenges are why many GraphQL server frameworks provide robust support for subscriptions, often abstracting away much of the underlying complexity for developers. GraphQL subscriptions complete the trifecta of interaction patterns, enabling a dynamic, reactive data flow that is essential for modern applications. By giving clients the ability to listen for changes, GraphQL empowers developers to build engaging, real-time user experiences that were previously much more difficult to achieve with traditional API designs. With an understanding of how to read, write, and listen to data through GraphQL, we're ready to explore the exciting journey of building the GraphQL server itself. Chapter 8. Building a GraphQL server. Hands-on with popular tools. Up to this point, we've explored GraphQL from both a conceptual and client-centric perspective. Understanding its purpose, its operational types, queries, mutations, subscriptions, and how to define its data structure, schema definition language. Now, it's time to go behind the scenes and understand how a GraphQL API actually works on the server side. Building a GraphQL server is essentially about creating an application that can receive GraphQL requests, queries, mutations, subscriptions, understand them based on a defined schema, fetch or manipulate the necessary data, and then return a structured JSON response. The role of a GraphQL server. At its core, a GraphQL server acts as an intelligent intermediary. It sits between your client applications and your various data sources. When a client sends a GraphQL request, the server performs several key functions. Parsing. It receives the incoming request, often a string of GraphQL formatted text, and parses it into an abstract syntax tree, AST, an internal, structured representation of the request. Validation. It validates the parsed request against the API's schema. This checks if the requested fields, arguments, and types are valid, and if the client is asking for something that the API actually supports. If not, it returns an error immediately. Execution. If the request is valid, the server then executes it. This is where the magic happens. It traverses the fields in the request and calls corresponding functions that know how to fetch or manipulate the actual data. Response generation. Finally, it gathers all the resolved data and formats it into the JSON structure that matches the client's original request. Crucially, a GraphQL server doesn't care where your data comes from. It can fetch data from traditional relational databases, like PostgreSQL, MySQL, NoSQL databases, like MongoDB, Cassandra, legacy REST APIs, microservices, third-party APIs, or even static files. This flexibility allows GraphQL to act as a powerful API gateway that unifies disparate data sources into a single, cohesive interface. The resolver. The data fetcher. At the heart of the GraphQL server's execution phase are resolvers. Think of resolvers as the explicit instructions for how to retrieve the data for each field in your schema. Every field in your schema, whether it's a field on a query type, a mutation type, or an object type, needs a corresponding resolver function. Let's revisit a simple schema. Type query. User ID, ID. User. Type user. ID name string email, string. Posts post. Type post. ID title string author user. When a client sends a query like this, query. User ID. 123. Name. Posts. Title. The server process would roughly look like this. the query user ID 123 part is executed. The server finds the user field on the query type and calls its resolver. This user resolver would typically take the id argument and fetch the user data, e.g., from a database. Once the user data is resolved, the server then looks at the nested fields requested, like name and posts. For name, if it's already part of the user object fetched by the user resolver, its resolver might be trivial, just returning the name property. For posts, the post resolver on the user type is called. This resolver usually receives the parent object, in this case, the user object that was just resolved, and might use the user's ID to fetch their associated posts, e.g., select from posts where authorid equals userid. Resolver functions typically receive 4 arguments: parent or root, the result of the parent field's resolver; args, an object containing the arguments passed to the current field, e.g., id; 123 for user ID; 123 context, a special object that is shared across all resolvers in a single GraphQL operation. This is ideal for passing things like database connections, authenticated user information, or logging utilities. Info, an object containing information about the execution state, including the parsed query ASD, schema, etc., mostly used for advanced scenarios. The context object is particularly useful for dependency injection and managing cross-cutting concerns. For example, your authentication middleware might populate the context with the authenticated user, and then every resolver can access context current user to perform authorization checks. Popular server-side frameworks. Building a GraphQL server from scratch involves a lot of boilerplate, parsing, validation, execution. Fortunately, there are robust frameworks in virtually every popular programming language that handle this complexity for you, allowing you to focus on your schema and resolvers. Here are a few prominent examples: JavaScript, TypeScript, Node.js, Apollo Server, arguably the most popular choice, offering a comprehensive and production-ready solution. It integrates well with various Node.js frameworks, Express, Koa, Happy, etc., and provides features like caching, authentication, and error handling. Apollo also provides Apollo Federation for building distributed GraphQL architectures. GraphQL.js, the reference implementation of GraphQL in JavaScript. While powerful, it's a lower-level library, and most developers will use a higher-level framework like Apollo Server or GraphQL Yoga built on top of it. Python, Graphene, a very popular framework for building GraphQL APIs in Python. It supports popular web frameworks like Django and Flask and allows you to build schemas using familiar Python classes. Ruby, GraphQL Ruby, the leading choice for Ruby developers, providing a well-structured and performant way to implement GraphQL. It's often used with Ruby on Rails applications. Java, Spring for GraphQL, integrates GraphQL capabilities directly into the popular Spring ecosystem, leveraging existing Spring data, Spring security, and other Spring features. GraphQL Java, a comprehensive library for implementing GraphQL in Java, often used as the underlying engine for higher-level frameworks. Go, GQLGen, a schema-first Go library that generates Go code from your GraphQL schema, making it type-safe and efficient. GraphQL Go, a more low-level, code-first approach for building GraphQL servers in Go. A conceptual walkthrough without code blocks. Let's imagine sketching out a basic GraphQL server using any asterisk of these frameworks. Define your schema. You'd start by writing your GraphQL schema using SDL. This outlines all your types, queries, mutations, and subscriptions. This is the contract for your API. Example, type query hello. String, set up the server instance. You then import your chosen framework, e.g., Apollo Server, and create an instance of it, passing in your schema. This framework handles the HTTP request listening and GraphQL parsing. Implement resolvers. For every field in your schema, especially those on query, mutation, and subscription types, you would write a resolver function. For hello, string, the resolver would simply return hello, GraphQL. Connect to data sources. If your resolvers need to fetch data, e.g. user, ID, user, This resolver would contain the logic to interact with your database, call another API, or access any other data source. This is where you might use an object relational mapper, ORM, like Sequelize.js, SQL Alchemy Python, or Hibernate Java to communicate with your database. Start the server. Finally, you'd start the server, making it listen for incoming GraphQL requests on a specific port. When a client sends a GraphQL query, the framework takes over. It parses the query string, validates it against your schema, maps the requested fields to your resolver functions, gathers the data returned by these resolvers, and packages it all into a single JSON response. Building a GraphQL server, while conceptually more involved than simply exposing database tables, offers unparalleled flexibility and efficiency. By acting as a unified API layer, it empowers front-end developers to consume data with unprecedented control, transforming the way modern applications are built and maintained. The next step, naturally, is to understand how these client applications actually consume the GraphQL API. Chapter 9: Consuming GraphQL, Client-Side Integration and Best Practices. We've now explored the what and how of GraphQL, what it is, why it matters, its core operations, schema definition, and even how to build a server. With a GraphQL API serving data, the next crucial step is to understand how client-side applications, whether a web app built with React, a mobile app for iOS or Android, or even another server, effectively consume this powerful interface. While you could technically consume a GraphQL API by simply sending raw HTTP post requests directly to your single GraphQL endpoint, this approach is quickly cumbersome and inefficient for anything beyond the simplest of applications. Imagine manually handling every request, managing loading states, caching data, and updating your user interface. It would quickly become a huge burden. This is where specialized GraphQL client libraries come into play. These libraries are designed to abstract away much of the complexity of communicating with a GraphQL server, providing developers with powerful tools for data fetching, caching, state management, and UI integration. They act as a sophisticated intermediary, optimizing the interaction between your application's components and your GraphQL API. The role of GraphQL client libraries. A robust GraphQL client library typically offers several key features that significantly improve the developer experience and application performance. Request execution. They handle the actual sending of GraphQL queries, mutations, and subscriptions over HTTP, for queries, mutations, and WebSockets for subscriptions, managing the network requests and responses. Caching. This is arguably one of the most powerful features. Client libraries often provide an intelligent, normalized cache. When data is fetched, it's stored in this cache. If the same data, or parts of it, is needed again, the client can serve it from the cache, eliminating unnecessary network requests and greatly speeding up your application. When data changes via a mutation, the cache can be automatically updated, ensuring UI consistency. State management. Many GraphQL clients integrate seamlessly with popular UI frameworks, like React, Vue, Angular, offering hooks or components that bind your UI directly to your GraphQL data. This simplifies complex data flows and allows your UI to react automatically to data changes. Loading and error handling. They provide convenient ways to track the loading state of your data and handle any errors that occur during the fetch, making it easier to build robust user interfaces that gracefully display loading spinners or error messages. Data normalization. Caching works best when data is normalized. Client libraries often store data in a flattened, normalized structure, removing redundancies and ensuring that if an object is updated, e.g., a user's name, that change is reflected wherever that user appears in your application. Optimistic UI updates. For mutations, sophisticated clients can allow you to implement optimistic UI updates. This means the client immediately updates the UI to reflect the expected result of a mutation, even before the server has confirmed the change. If the server later indicates an error, the UI can revert. This provides a snappier, more responsive user experience. Popular client-side libraries. Just like with server frameworks, there are several excellent client libraries available across different programming languages and frameworks. Apollo Client. This is, without a doubt, the most popular and feature-rich GraphQL client, particularly for web applications built with React, Vue, and Angular. It offers powerful caching, state management with React hooks, and easy integration with Redux or other state solutions. Apollo Client's ecosystem extends to other parts of the development workflow, making it a comprehensive choice. Relay, developed by Facebook, Relay is another robust GraphQL client, primarily focused on React. It's known for its strong performance optimizations and compile-time validation, but it can have a steeper learning curve than Apollo Client. Urkel, a lightweight, highly customizable, and extensible GraphQL client. It's gaining popularity for its simplicity and flexibility, making it a good choice for those who want more control over their client's behavior and performance. GraphQL Request, a minimalist GraphQL client that simply sends GraphQL documents and variables over HTTP. It's often used for simple requests or as a base for building custom client logic. Language-specific SDKs. For mobile development, e.g., Swift Kotlin or desktop applications, dedicated SDKs, like Apollo iOS Android, provide type-safe ways to interact with GraphQL, often integrating with the platform's native UI frameworks. Example, consuming with Apollo Client, conceptual. Let's imagine a React component that needs to display a user's name and email, and possibly update their email, using Apollo Client. Your application would typically be wrapped with an Apollo Provider component, which makes the Apollo Client instance available to all child components. 1. Fetching data with useQuery conceptual. Inside a component that needs user data. Imagine this is a React functional component. Import useQuery GQL from @Apollo Client. Const gtusrprfile equals GQL. Query get user profile, $user ID. ID. User ID, userid. Name. Email. Posts. Title. Function user profile, userid. Const loading error data equals useQuery get user profile. Variables, userid. If loading, return p-loading user profile. P. If error, return p-error. Error message /p. Data is available in data.user. Const user equals data. Return. Div. h2user.name/h2. P-email, user email/p. h3 posts /h3. ul. User posts map post. Leaky equals post ID post title /lie. ul. Div. In this conceptual example, useQuery automatically handles the network request, loading state via loading, and error state via error. Once the data is fetched, it's available in the data object, and the component re-renders with the user's information. The data for user and posts would also be intelligently stored in Apollo Client's cache. 2. Updating data with use mutation, conceptual. To update a user's email. Import use mutation, GQL from @Apollo Client. Const updateUserEmail equals GQL. Mutation update user email, $user ID. ID, new email, string. Update user ID. Userid email, new email. Id, email. Function email updater, userid current email. Const update email, loading error, equals use mutation update user email. Const handle submit equals async, event equals. Event prevent default, const new email equals event target element cmail input value, try. This will send the mutation to the server. Await update email. Variables. Userid new email. Optional, update the cache directly after mutation. Update cache data equals. Const updated user equals data update user. Cache modify. Id. Cache identify updated user. Generate a cache ID for the user. Fields. Email. Return updated user email. Update email field in cache. Alert, email updated successfully. Catch E. Console error, error updating email. E. Return. Form on submit equals handle submit. Input type equals email, name equals email input, default value equals current email. Button type equals submit, disabled equals loading. Loading. Updating, update email. Button. Error end in P error updating email. Error message /p. Form. Here, use mutation returns a function, update email, that you call to trigger the mutation. The update function provided to use mutation is a powerful Apollo client feature that allows you to manually update the cache after a mutation, ensuring that related queries in your app reflect the change immediately without refetching. Beyond the library, client-side best practices, authentication and authorization. While the GraphQL server handles the core logic, clients need to securely send authentication credentials, e.g., JWT tokens in the HTTP headers using a client's link or middleware. The client then processes the server's authorization responses to manage UI access. Error handling. Design your UI to gracefully handle and display errors. GraphQL clients often provide hooks or mechanisms to catch network errors, validation errors, and custom business logic errors returned by your GraphQL API. Loading states. Implement clear loading indicators, spinners, skeleton loaders, while data is being fetched to improve perceived performance and user experience. Code generation. For statically typed languages, TypeScript, Swift, Kotlin, many GraphQL clients offer code generation tools. These tools read your GraphQL schema and queries and generate type-safe code for your client, catching bugs at compile time and providing excellent auto-completion. Tooling. Use development tools like GraphQL Playground or GraphQL in your browser. These interactive environments allow you to explore your API schema, write queries, and test your API responses, greatly accelerating client development and debugging. Consuming a GraphQL API effectively transforms the development process. By leveraging powerful client libraries and adhering to best practices, developers can build reactive, performant, and delightful user experiences, simplifying data management and focusing more on the creative aspects of application development. With the flow from server to client now understood, we're ready to explore how to optimize and secure these powerful APIs for real-world production use. Chapter 10. Beyond the Basics. Performance, Security, and the Future of GraphQL. You've journeyed through the fundamentals of GraphQL, from its core operations and schema definition to building a server and consuming its data from the client. As with any powerful technology, truly harnessing GraphQL's potential in production environments requires understanding advanced considerations. How to optimize its performance, ensure its security, and manage its evolution over time. Performance optimization, making your API blazing fast. While GraphQL inherently solves problems like overfetching and underfetching, poor implementation can lead to new performance bottlenecks. The N+1 problem and data loaders. This is one of the most common performance traps in GraphQL. If fetching a list of users, N items, requires a separate database query for each user's details, you end up with N+1 queries. Data loaders, a concept popularized by Facebook and implemented in various languages, like DataLoader.js in Node.js, provide a simple yet powerful solution. They batch and cache requests to your backend data sources, effectively turning N separate queries into a single, optimized lookup or batch job. This is crucial for high-performance GraphQL APIs. Caching strategies. Server-side caching. Implement caching at various layers of your server. This could be database query caching, object caching, e.g., RIDIs for frequently accessed objects, or even full response caching for static queries, though this is less common with GraphQL's dynamic nature. Client-side caching. As discussed in Chapter 9, client libraries like Apollo Client provide intelligent, normalized caches that drastically reduce redundant network requests and improve UI responsiveness. Query complexity and depth limiting. Malicious or accidentally complex queries can overwhelm your server. Depth limiting prevents queries from being nested too deeply, limiting the number of subselections. Query cost analysis assigns a cost to each field in your schema, e.g., fetching a list of 100 items might cost more than fetching a single item. The server then calculates the total cost of an incoming query and rejects it if it exceeds a predefined threshold. Persisted queries. Instead of sending the full GraphQL query string over the network every time, clients can send a compact ID or hash. The server stores the full query string associated with that ID. This reduces network payload size, improves caching opportunities, and can even act as a security measure by only allowing pre-approved queries. Security, protecting your data. A GraphQL API, like any API, is an entry point to your valuable data. Robust security measures are paramount. Authentication versus authorization. Authentication. Verify the identity of the user making the request. This is typically done at the HTTP request level, e.g., using JWT tokens in the authorization header before the GraphQL query is even parsed. Authorization. Determine if the authenticated user has permission to access or modify specific data or fields. This is typically handled within your resolvers. For example, a user resolver might check if the authenticated user has the necessary role, admin, contributor, customer, to access sensitive fields like email or payment info. You might also implement field-level authorization to allow a user to see some fields of an object, but not others. Input validation. Always validate input arguments, sent in queries and mutations, on the server side. Never trust client-side validation. This is essential to prevent common vulnerabilities like SQL injection or cross-site scripting, XSS. Rate limiting. Protect your API from abuse or denial of service, DoS, attacks by limiting the number of requests a client can make within a certain timeframe. This can be done at the HTTP level or specifically tied to GraphQL operations. Error handling. Be cautious about the information exposed in error messages. Detailed stack traces or internal server errors can inadvertently leak sensitive information. Configure your server to return generic, user-friendly error messages in production. Sensitive data exposure. Ensure sensitive data, e.g., passwords, API keys, is never exposed, even if a client accidentally requests it in a query. Your resolvers should explicitly prevent access to such fields unless explicitly authorized and handled securely. Schema evolution, adapting to chain. One of GraphQL's major strengths is its ability to evolve an API without breaking existing clients. Non-breaking changes, adding new fields and types. Existing clients will simply ignore them. Adding nullable fields to existing types, existing clients will continue to work. Adding new queries, mutations, subscriptions, clients can adopt them at their leisure. Deprecation. When you need to phase out a field or enum value, mark it as @deprecated in your schema. This signals to clients that it will eventually be removed and encourages them to migrate to newer alternatives, while still allowing older clients to function without breaking. Version management. While GraphQL aims to avoid explicit API versioning, v1, v2, for significant breaking changes, you might need to launch a new GraphQL endpoint, or more commonly, use techniques like schema stitching, combining multiple smaller GraphQL schemas into one larger, unified schema. GraphQL federation, e.g., Apollo federation, a more advanced approach where multiple independent GraphQL backends, called subgraphs, compose a single, unified supergraph API. This allows large organizations to build and maintain separate services while exposing a single, coherent API to clients. This is how large, distributed teams can scale their API development. The GraphQL ecosystem and future trends. The GraphQL ecosystem is vibrant and continually expanding. Code generation. Tools that read your schema and automatically generate type definitions, client-side query methods, or even server-side resolver boilerplate in various programming languages. This streamlines development and ensures type safety. Database integrations. Projects that automatically generate GraphQL APIs from your database schema, e.g., Hasura, PostgreSQL, accelerating development for data-rich applications. Testing. Evolving best practices and tools for testing GraphQL APIs, from unit tests for resolvers to end-to-end tests that simulate client requests. Cloud services. Major cloud providers, AWS AppSync, Azure API for GraphQL, Google Cloud Endpoints, now offer managed GraphQL services, handling much of the server infrastructure for you. The future of GraphQL looks bright. It continues to gain enterprise adoption, and the specification itself is being extended to incorporate new features like defer and stream directives for more advanced data fetching patterns. It's evolving towards being a universal query language for any data source, not just typical HTTP APIs. GraphQL vs REST Revisited. When to choose which. While this book champions GraphQL, it's not a silver bullet. Knowing when to choose GraphQL over REST, or even use them together, is crucial. Choose GraphQL when you have diverse client needs, mobile, web, third-party integrations, that require different data shapes from the same backend. You need to reduce network round trips and optimize payload sizes, especially for mobile clients or high-latency environments. You have a complex, interconnected data model, a graph of data. You prioritize rapid iteration and independent development for front-end teams. You need real-time updates, subscriptions. You are building an API gateway to unify disparate microservices or legacy systems. Consider REST when your API is resource-oriented and simple, with well-defined resources and actions, e.g., a simple CRUD API for a single entity. You are primarily dealing with document-centric data and less about complex relationships. Your existing backend infrastructure is heavily invested in REST, and adapting it to GraphQL would require a prohibitive refactor. You need to handle simple file, uploads, downloads, or standard webhooks. In many modern architectures, you might even see a hybrid approach, using GraphQL as a powerful facade over an array of internal REST services, or using both side by side for different parts of an application. GraphQL is more than just a passing trend. It's a mature, powerful, and flexible approach to API design that addresses many of the challenges of contemporary software development. By understanding its core principles, mastering its implementation, and applying advanced techniques for performance and security, you are now well equipped to leverage this modern API handbook for your own projects and contribute to the next wave of API innovation.